proposed to use this effect to disable an enemy's military and civilian infrastructure as an adjunct to other nuclear or conventional military operations. By itself, it could as well be useful to terrorists for crippling a nation's economic electronics-based infrastructure. Because the effect is most effectively produced by high-altitude nuclear detonations, by military weapons delivered by air, though ground bursts also produce EMP effects over a localized area, it can produce damage to electronics over a wide, even continental, geographical area. Research has been done into the possibility of pure fusion bombs, nuclear weapons that consist of fusion reactions without requiring a fission bomb to initiate them. Such a device might provide a simpler path to thermonuclear weapons than one that required the development of fission weapons first, and pure fusion weapons would create significantly less nuclear fallout than other thermonuclear weapons because they would not disperse fission products. In 1998, the United States Department of Energy divulged that the United States had made a substantial investment in the past to develop pure fusion weapons, but that the U.S. does not have and is not developing a pure fusion weapon, and that no credible design for a pure fusion weapon resulted from the DOE investment. Nuclear isomers provide a possible pathway to fissionless fusion bombs. These are naturally occurring isotopes, 178 Miller HEF being a prominent example, which exist in an elevated energy state. Mechanisms to release this energy as bursts of gamma radiation, as in the hafnium controversy, have been proposed as possible triggers for conventional thermonuclear reactions. Antimatter, which consists of particles resembling ordinary matter particles in most of their properties but having opposite electric charge, has been considered as a trigger mechanism for nuclear weapons. A major obstacle is the difficulty of producing antimatter in large enough quantities, and there is no evidence that it is feasible beyond the military domain. However, the U.S. Air Force funded studies of the physics of antimatter in the Cold War and began considering its possible use in weapons, not just as a trigger, but as the explosive itself. A fourth-generation nuclear weapon design is related to, and relies upon, the same principle as antimatter-catalyzed nuclear pulse propulsion. Most variation in nuclear weapon design is for the purpose of achieving different yields for different situations, and in manipulating design elements to attempt to minimize weapon size, radiation hardness, or requirements for special materials, especially fissile fuel or tritium. Tactical nuclear weapons. Some nuclear weapons are designed for special purposes. Most of these are for non-strategic, decisively war-winning purposes and are referred to as tactical nuclear weapons. The neutron bomb purportedly conceived by Sam Cohen is a thermonuclear weapon that yields a relatively small explosion, but a relatively large amount of neutron radiation. Such a weapon could, according to tacticians, be used to cause massive biological casualties while leaving inanimate infrastructure mostly intact and creating minimal fallout. Because high-energy neutrons are capable of penetrating dense matter, such as tank armor, neutron warheads were procured in the 1980s, though not deployed in Europe, for use as tactical payloads for U.S. Army artillery shells, 200mm 79 and 155mm W-82, and short-range missile forces. Soviet authorities announced similar intentions for neutron warhead deployment in Europe. Indeed, they claim to have originally invented the neutron bomb, but their deployment on USSR tactical nuclear forces is unverifiable. A type of nuclear explosive most suitable for use by ground special forces was the Special Atomic Demolition Munition, or SAD-M, sometimes popularly known as a suitcase nuke. This is a nuclear bomb that is man-portable, or at least truck-portable, and though of a relatively small yield, 1 or 2 kilotons, is sufficient to destroy important tactical targets such as bridges, dams, tunnels, important military or commercial installations, etc., either behind enemy lines or preemptively on friendly territory soon to be overtaken by invading enemy forces. These weapons require plutonium fuel and are particularly dirty. They also demand especially stringent security precautions in their storage and deployment. Small, tactical, nuclear weapons were deployed for use as anti-aircraft weapons. Examples include the USAF Air-2 Genie, the AIM-26 Falcon, and U.S. Army Nike Hercules. Missile interceptors such as the Sprint and the Spartan also used small nuclear warheads, optimized to produce neutron or X-ray flux, but were for use against enemy strategic warheads. Other small or tactical nuclear weapons were deployed by naval forces for use primarily as anti-submarine weapons. These included nuclear depth bombs or nuclear-armed torpedoes. Nuclear mines for use on land or at sea are also possibilities. Weapons delivery. The system used to deliver a nuclear weapon to its target is an important factor affecting both nuclear weapon design and nuclear strategy. The design, development, and maintenance of delivery systems are among the most expensive parts of a nuclear weapons program. They account, for example, for 57% of the financial resources spent by the United States on nuclear weapons projects since 1940. The simplest method for delivering a nuclear weapon is a gravity bomb dropped from aircraft. This was the method used by the United States against Japan in 1945. This method places few restrictions on the size of the weapon. It does, however, limit attack range, response time to an impending attack, and the number of weapons that a country can field at the same time. With miniaturization, nuclear bombs can be delivered by both strategic bombers and tactical fighter bombers. This method is the primary means of nuclear weapons delivery. The majority of U.S. nuclear warheads, for example, are free-fall gravity bombs, namely the B-61, which is being improved upon to this day. Preferable from a strategic point of view is a nuclear weapon mounted on a missile, which can use a ballistic trajectory to deliver the warhead over the horizon. Although even short-range missiles allow for a faster and less vulnerable attack, the development of long-range intercontinental ballistic missiles, ICBMs, and submarine-launched ballistic missiles, SLBMs, has given some nations the ability to plausibly deliver missiles anywhere on the globe with a high likelihood of success. More advanced systems, such as multiple independently targetable re-entry vehicles, MIRVs, can launch multiple warheads at different targets